1, and the lecture on symmetric matrices. So that's the most important class of matrices, symmetric matrices. A equals A transpose. So the first points, the main points of the lecture, I'll tell you right away. What's special about the eigenvalues? What's special about the eigenvectors? This is the way we now look at a matrix. We want to know about its eigenvalues and eigenvectors. And if we have a special type of matrix, that should tell us something about eigenvalues and eigenvectors. Like Markov matrices, they had an eigenvalue equal 1. Now, symmetric matrices. Can I just tell you right off what the main facts, the two main facts are? The eigenvalues of a symmetric matrix, real. This is a real symmetric matrix. We're talking mostly about real matrices. The eigenvalues are also real. So our examples of rotation matrices where we got eigenvalues that were complex, that won't happen now. For symmetric matrices, the eigenvalues are real, and the eigenvectors are also very special. The eigenvectors are perpendicular, orthogonal. So which do you prefer? I'll say perpendicular. Well, they're both long words. Perpendicular. Okay, right. So, you should say why, and I'll at least answer why for case 1. Maybe case 2, the checking that the eigenvectors are perpendicular, I'll leave to the book. But let's just realize what, well, first I have to say, it could happen like for the identity matrix. There's a symmetric matrix. Its eigenvalues are certainly all real. They're all 1 for the identity matrix. What about the eigenvectors? Well, for the identity, every vector is an eigenvector. So how can I say they're perpendicular? What I really mean is this word R should really be written can be chosen perpendicular. That is, if we have, it's the usual case. If the eigenvalues are all different, then each eigenvalue has one line of eigenvectors, and those lines are perpendicular here. But if an eigenvalue is repeated, then there's a whole plane of eigenvectors, and all I'm saying is that in that plane, we can choose perpendicular ones. So that's why it's a can be chosen part. This is in the case of a repeated eigenvalue where there's some real substantial freedom. But the typical case is different eigenvalues, all real, one-dimensional eigenvector spaces, eigenspaces, and all perpendicular. So let's just see the conclusion. If we accept those as correct, what happens, and I also mean that there's a full set of them. So that's part of this picture here, that there's a complete set of eigenvectors, perpendicular ones. So having a complete set of eigenvectors means, so normal, so the usual, maybe I put the usual case is that the matrix A we can write in terms of its eigenvalue matrix and its eigenvector matrix this way, right? We can do that in the usual case. But now what's special when the matrix is symmetric? So this is the usual case. And now let me go to the symmetric case. So in the symmetric case, A, this should become somehow a little special. Well, the lambdas on the diagonal are still on the diagonal. They're real, but that's where they are. What about the eigenvector matrix? So what can I do now special about the eigenvector matrix? When the A itself is symmetric, that says something good about the eigenvector matrix. So what does this lead to? These perpendicular eigenvectors. I can not only guarantee they're perpendicular, I could also make them unit vectors. No problem. Just scale their length to 1. So what do I have? I have orthonormal eigenvectors. And what does that tell me about the eigenvector matrix? What letter should I now use in place of S? Remember, S has the eigenvectors in its columns, but now those columns are orthonormal. So the right letter to use is Q. So so we've got the letter all set up, so this should be Q lambda Q inverse. Q standing in our minds always for this matrix. In this case, it's square. So these are the columns of Q, of course. And one more thing. What's Q inverse? For a matrix that has these orthonormal columns, we know that the inverse is the same as the transpose. So here is the beautiful, there's the great description, the factorization of a symmetric matrix. And this is like one of the famous theorems of linear algebra, that if I have a symmetric matrix, it can be factored in this form, an orthogonal matrix times diagonal times the transpose of that orthogonal matrix. And of course, everybody immediately says, yes, and if this is possible, then that's clearly symmetric, right? We've looked at products of 3 guys like that and taken their transpose, and we got it back again. So you see the beauty of this factorization then. It completely displays the eigenvalues and eigenvectors and the symmetry of the whole thing, because that product, Q times lambda times Q transpose, if I transpose it, it just comes in this position and we get that matrix back again. So that's, in mathematics, that's called the spectral theorem. Spectrum is the set of eigenvalues of a matrix. It somehow comes from the idea of the spectrum of light as a combination of pure things, where our matrix is broken down into pure eigenvalues and eigenvectors. In mechanics, it's often called the principal axis theorem. It's very useful. It means that if you have, we'll see it geometrically. It means that if I have some material, if I look at the right axes, it becomes diagonal. It becomes, the directions don't couple together. Okay, so that's what to remember from this lecture. Now, I would like to say, why are the eigenvalues real? Can I do that? So because something useful comes out. So I'll just come to that question. Why real eigenvalues? Okay. So I have to start from the only thing we know, AX equal lambda X. Okay. But as far as I know at this moment, lambda could be complex. I'm going to prove it's not. And X could be complex. In fact, for the moment, even A could be. We could even think, well, what happens if A is complex? Well, one thing we can always do, this is like always okay. If I have an equation, I can take the complex conjugate of everything. so A conjugate X conjugate equal lambda conjugate X conjugate. It just means that everywhere over here that there was an I, then here I changed it to a minus I. You know that step, that conjugate business, that A plus IB, if I conjugate it, it's A minus IB. That's the meaning of conjugate. And products behave right. I can conjugate every factor. So I haven't done anything yet except to say what would be true if X, in any case, even if X and lambda were complex. Of course, we're speaking about real matrices A, so I can take that out. Actually, this already tells me something about real matrices. I haven't used any assumption of A equal A transpose yet. Symmetry is waiting in the wings to be used. This tells me that if a real matrix has an eigenvalue lambda and an eigenvector x, it also has another of its eigenvalues is lambda bar with eigenvector x bar. Real matrices, the eigenvalues come in lambda, lambda bar. The complex eigenvalues come in lambda and lambda bar pairs. But of course, I'm aiming to show that they're not complex at all here by getting symmetry in. So how am I going to use symmetry? I'm going to transpose this equation to x bar transpose A transpose equals x bar transpose lambda bar. That's just a number, so I don't mind where I put that number. This is then again okay. But now I'm ready to use symmetry. I'm ready. So this was all just mechanics. Now comes the moment to say, okay, if the matrix is symmetric, then this A transpose is the same as A. You see, at that moment I used the assumption. Now let me finish the discussion. Here's the way I finish. I look at this original equation, and I take the inner product. I multiply both sides by, oh, maybe I'll do it with this one. I multiply both sides by x bar transpose. X bar transpose A x bar equals lambda bar x bar transpose x bar. Okay, fine. All right. Now, what's the other one? Oh, the other one I'll probably use this guy. Am I happy about this? No, for some reason I'm not. I want to, yeah, if I take the inner product of this from the right with x bar, I get x bar transpose A x bar equals x bar transpose lambda bar x bar. I've done something dumb because I've got I haven't learned anything. I've got those two equations are identical. So forgive me for doing such a thing, but I'll look at the book. Okay. So I took the dot product. Yeah, somehow it didn't. I should have taken the dot product of this guy here with, that's what I was going to do. AX equals lambda x bar transpose x, right? Okay, so that's fine. That comes directly from that, multiplying both sides by x bar transpose. But now I'd like to get, why do I have x bars over there? Oh, yes. Forget this. Okay, on this one, right. On this one, I took it like that. I multiply on the right by x. That's the idea. Okay. Now, why am I happier with this situation now? A proof is coming here. Because I compare this guy with this one. And they have the same left-hand side. So they have the same right-hand side. So comparing those two, I'll raise the board to do this comparison. This thing, lambda x bar transpose x, is equal to lambda bar x bar transpose x. Okay. And the conclusion I'm going to reach, am I on the right track here? The conclusion I'm going to reach is lambda equal lambda bar. I would have to track down the other possibility that this thing is 0. But let me, oh yeah, that's important. It's not 0. So once I know that this isn't 0, I just cancel it, and I learn that lambda equals lambda bar. And so what? Have you got the reasoning all together? What does this tell us? Lambda is an eigenvalue of this symmetric matrix. We've just proved that it equaled lambda bar, so we have just proved that lambda is real, right? If a number is equal to its own complex conjugate, then there's no imaginary part at all. The number is real. So lambda is real. Good. Good. Now, but it depended on this little expression, on knowing that that wasn't 0, so that I could cancel it out. So can we just take a second on that one? Because it's an important quantity. X bar transpose x. Okay, now remember, as far as we know, x is complex. So this is, here, x is complex. X has these components, x1, x2, down to xn. And x bar transpose, well, it's transposed and it's conjugated. So that's x1 conjugated, x2 conjugated, up to xn conjugated. I'm really reminding you of crucial facts about complex numbers that are going to come into the next lecture as well as this one. So what can you tell me about that product? I guess what I'm trying to say is, if I had a complex vector, this would be the quantity I would like. This is the quantity I like. I would take the vector times its transpose. Now, what happens usually if I take a vector, x transpose x? I mean, that's a quantity we see all the time, x transpose x. That's the length of x squared, right? That's this positive length squared. It's Pythagoras. It's x1 squared plus x2 squared, and so on. Now, our vector is complex, and you see the effect? I'm conjugating one of these guys. So now when I do this multiplication, I have x1 bar times x1, and x2 bar times x2, and so on. So this is some a plus ib, and this is some a minus ib. I mean, what's the point here? What's the point when I multiply a number by its conjugate, a complex number by its conjugate? What do I get? I get the imaginary part is gone. When I multiply a plus ib by its conjugate, what's the result of that, of each of those separate little multiplications? There's an a squared, and what's b squared? It comes in with a plus or a minus? A plus. I times minus I is a plus b squared. And what about the imaginary part? Gone, right? An IAB and a minus IAB. So this is the right thing to do. If you want a decent answer, then multiply numbers by their conjugates. multiply vectors by the conjugates of X transpose. So this quantity is positive, this quantity is positive, the whole thing is positive, except for the 0 vector. And that allows me to know that this is a positive number, which I safely cancel out, and I reach the conclusion. So actually, in this discussion here, I've done two things. I reached the conclusion that lambda is real, which I wanted to do. But at the same time, we sort of saw what to do if things were complex. If a vector is complex, then it's x bar transpose x. This is its length squared. And as I said, the next lecture, Monday, will repeat that this is the right thing and then do the right thing for matrices and all other complex possibilities. Okay. But the main point then is that the eigenvalues of a symmetric matrix, where did we use symmetry, by the way? We used it here, right? Can I just, suppose A was a complex. Suppose A had been a complex number. Could I have made all this work? If A was a complex number, complex matrix, then here I should have written A bar. I erased the bar because I assumed A was real. But now let's suppose for a moment it's not. Then when I took this step, what should I have? What did I do on that step? I transposed. So I should have A bar transpose. In the symmetric case, that was A. And that's what made everything work, right? This led immediately to that. This one led immediately to this when the matrix was real, so that didn't matter, and it was symmetric, so that didn't matter. Then I got A. But, so now I just get to ask you, suppose the matrix had been complex, what's the right equivalent of symmetry? So the good matrix, so here, let me say, good matrices. By good, I mean real lambdas and perpendicular x's. And tell me now which matrices are good. If they're real matrices, the good ones are symmetric, because then everything went through. I'm saying now what's good. These are the good matrices. They have real eigenvalues, perpendicular eigenvectors. Good means A equal A transpose, if real. Then that was what our proof worked. But if A is complex, our proof will still work provided A bar transpose is A. Do you see what I'm saying? I'm saying if we have complex matrices, and we want to say, are they as good as symmetric matrices? Then we should not only transpose the thing, but conjugate it. Those are good matrices. And of course, the most important case is when they're real, this part doesn't matter, and I just have A equal A transpose symmetric. I'll just repeat that. The good matrices, if complex, are these. If real, that doesn't make any difference, so I'm just saying symmetric. And of course, 99% of examples and applications, the matrices are real, and we don't have that, and then symmetric is the key property. Okay. So that's these main facts. And now let me just, so that's this x bar transpose x. Okay. So I'll just write it once more in this form. So perpendicular orthonormal eigenvectors, real eigenvalues, transposes of orthonormal eigenvectors. That's the symmetric case, A equal A transpose. Okay. Good. Actually, I'll even take one more step here. Suppose I can break this down to show you really what that says about a symmetric matrix. I can break that down. Let me, here go these eigenvectors. Here go these eigenvalues, lambda 1, lambda 2, and so on. Here go these eigenvectors transposed. And what happens if I actually do out that multiplication? Do you see what will happen? There's lambda 1 times q1 transpose. So the first row here is just lambda 1 q1 transpose. If I multiply column times row, you remember I could do that? When I multiply matrices, I can multiply columns times rows. So when I do that, I get lambda 1 and then the column and then the row, and then lambda 2 and the column and the row. Every symmetric matrix breaks up into these pieces. So these pieces have real lambdas, and they have these orthonormal eigenvectors. And maybe you even could tell me what kind of a matrix have I got there. Suppose I take a unit vector times its transpose. So column times row, I'm getting a matrix. That's a matrix with a special name. What kind of a matrix is it? We've seen those matrices now in Chapter 4. It's A transpose with a unit vector, so I don't have to divide by A transpose A. That matrix is a projection matrix. That's a projection matrix. It's symmetric, and if I square it, there'll be a Q1 transpose Q1, which is 1. So I'll get that matrix back again. Every symmetric matrix, every symmetric matrix is a combination of mutually perpendicular, so perpendicular projection matrices. Projection matrices. Okay. That's another way that people like to think of the spectral theorem, that every symmetric matrix can be broken up that way. I guess at this moment, first I haven't done an example. I could create a symmetric matrix, check that find its eigenvalues, they would come out real, find its eigenvectors, they would come out perpendicular, and you would see it in numbers, but maybe I'll leave it here for the moment in letters. Oh, maybe I will do it with numbers for this reason, because there's one more remarkable fact. Can I just put this further great fact about symmetric matrices on the board? When I have symmetric matrices, I know their eigenvalues are real. So then I can get interested in the question, are they positive or negative? And you remember why that's important. For differential equations, that decides between instability and stability. So after I know they're real, then the next question is, are they positive, are they negative? And I hate to have to compute those eigenvalues to answer that question. Right? Because computing the eigenvalues of a symmetric matrix of order, let's say 50, compute its 50 eigenvalues, is a job. I mean, by pencil and paper, it's a lifetime's job. I mean, and in fact, a few years ago, well, say 20 years ago, or 30, nobody really knew how to do it. I mean, so like science was stuck on this problem. If you have a matrix of order 50 or 100, how do you find its eigenvalues? Numerically now, I'm just saying, because pencil and paper is, we're going to run out of time or paper or something before we get it. Well, and you might think, okay, get MATLAB to compute the determinant of lambda minus a minus lambda I, this polynomial of 50th degree, and then find the roots. MATLAB will do it, but it will complain because it's a very bad way to find the eigenvalues. I'm sorry to be saying this, because it's the way I taught you to do it, right? I taught you to find the eigenvalues by doing that determinant and taking the roots of that polynomial. But now I'm saying, okay, I really meant that for 2 by 2s and 3 by 3s, but I didn't mean you to do it on a 50 by 50. And you're not too unhappy, probably, because you didn't want to do it. But good, because it would be a very unstable way. The 50 answers that would come out would be highly unreliable. So new ways are much better to find those 50 eigenvalues. That's a part of numerical linear algebra. But here's the remarkable fact, that MATLAB would quite happily find the 50 pivots, right? Now, the pivots are not the same as the eigenvalues. But here's the great thing. If I had a real matrix, I could find those 50 pivots, and I could see maybe 28 of them are positive and 22 are negative pivots. And I can compute those safely and quickly. And the great fact is that 28 of the eigenvalues would be positive and 22 would be negative. That the signs of the pivots, so this is like I hope you think this is kind of a nice thing, that the signs of the pivots for symmetric, I'm always talking about symmetric matrices. So I'm really like trying to convince you that symmetric matrices are better than the rest. So the signs of the pivots are same as the signs of the eigenvalues. The same number. The number of pivots greater than 0, the number of positive pivots is equal to the number of positive eigenvalues. So that actually is a very useful, that gives you a good start on a decent way to compute eigenvalues. Because you can narrow them down. You can find out how many are positive, how many are negative. Then you could shift the matrix by 7 times the identity. That would shift all the eigenvalues by 7. Then you could take the pivots of that matrix, and you would know how many eigenvalues of the original were above 7 and below 7. So this neat little theorem that the symmetric matrices have this connection between, nobody's mixing up and thinking the pivots are the eigenvalues. I mean, the only thing I can think of is the product of the pivots equals the product of the eigenvalues. Why is that? So if I asked you for the reason on that, why is the product of the pivots for a symmetric matrix the same as the product of the eigenvalues? Because they both equal the determinant. Right. The product of the pivots gives the determinant if no row exchanges. The product of the eigenvalues always gives the determinant. So the products, but that doesn't tell you anything about the 50 individual ones, which this does. Okay. So that's, those are essential facts about symmetric matrices. Okay. Now, I said in the lecture description that I would take the last minutes to start on positive definite matrices, because we're right there. We're ready to say what's a positive definite matrix. It's symmetric, first of all. Always I will mean symmetric. So this is the next section of the book. It's about this. If symmetric matrices are good, which is like the point of my lecture so far, then positive definite matrices are a subclass that are excellent. Okay, just the greatest. Okay. So what are they? They're matrices, they're symmetric matrices, so all their eigenvalues are real. You can guess what they are. These are symmetric matrices with all the eigenvalues are, okay, tell me what to write. What? Well, it's hinted, of course, by the name for these things. All the eigenvalues are positive. Okay. Tell me about the pivots. We can check the eigenvalues or we can check the pivots. All the pivots are what? And then I'll finally give an example. I feel awful that I have got to this point in the lecture and I haven't given you a single example. So let me give you one. 5, 3, 2, 2. That's symmetric. Fine. Its eigenvalues are real, for sure. But more than that, I know the signs of those eigenvalues. And also, I know the signs of those pivots. So what's the deal with the pivots? If the eigenvalues are all positive, and if this little fact is true that the pivots and eigenvalues have the same signs, then this must be true. All the pivots are positive. And that's the good way to test. This is the good test because what are the pivots for that matrix? The pivots for that matrix are 5. So pivots are 5. And what's the second pivot? Have we, noticed the formula for the second pivot in a matrix? It doesn't necessarily, it may come out a fraction for sure. But what is that fraction? Can you tell me? Well, here. The product of the pivots is the determinant. What's the determinant of this matrix? 11. So the second pivot must be 11 over 5, so that the product is 11. They're both positive. Then I know that the eigenvalues of that matrix are both positive. What are the eigenvalues? Well, I've got to take the roots of, do I put in a minus lambda? Do you mentally do this? Lambda squared minus how many lambdas? 8, right? 5 and 3. The trace comes in there. Plus, what number comes here? The determinant, the 11. So I set that to 0. So the eigenvalues are, let's see, half of that is 4. Look at that positive number, plus or minus the square root of 16 minus 11, I think 5. The eigenvalues, well, 2 by 2, they're not so terrible, but they're not so perfect. Pivots are really simple. And this is the family of matrices that you really want in differential equations because you know the signs of the eigenvalues, so you know the stability or not. Okay, there's one other related fact I can pop in here in the time available for positive definite matrices. The related fact is to ask you about determinants. So what's the determinant? What can you tell me if remember, positive definite means all eigenvalues are positive, all pivots are positive. So what can you tell me about the determinant? It's positive too. But somehow that's not quite enough. Here's a matrix, -1, -3. What's the determinant of that guy? It's positive, right? Is this a positive definite matrix? Are the pivots, what are the pivots? Well, negative. What are the eigenvalues? Well, they're also the same. So somehow I don't just want the determinant of the whole matrix. Here is 11, that's great. Here the determinant of the whole matrix is 3, that's positive. I've got to check like little subdeterminants. Say maybe coming down from the left. So the 1 by 1 and the 2 by 2 have to be positive. So that's where I get the all. All, can I call them subdeterminants? Are, see, I need to make the thing plural. I need to test n things, not just the big determinant. All subdeterminants are positive. Then I'm okay. Then I'm okay. This passes the test. 5 is positive and 11 is positive. This fails the test because that -1 there is negative. And then the big determinant is +3. So this fact, you see that actually the course like coming together. And that's really my point. Now, in this lecture, and particularly next Wednesday and Friday, the course comes together. These pivots that we met in the first week, these determinants that we met in the middle of the course, these eigenvalues that we met most recently. All matrices are square here. So coming together for square matrices means these 3 pieces come together, and they come together in that beautiful fact that if I have one of these, I have the others. But for symmetric matrices. So this will be the positive definite section, and then the real climax of the course is to make everything come together for m by n matrices, not necessarily symmetric. Bring everything together there, and that will be the final thing. Okay, so have a great weekend, and don't forget symmetric matrices. Thanks.